so that you can go back and catch up with it when you have the handout. All right, guys. So let's take a look at this gas loss simulator. And you'll see that we have some variables that we're going to be looking at. We're going to look at temperature and what is the K? So it's, all right, it's not Celsius, it's not Fahrenheit, it's in Kelvin. And we've got pressure that's measured in atmospheres. And we have two different gases, one that has small particles, and one that has, gas B has larger particles. And and we have volume, and volume is measured in liters. Now on your paper, you see the ideal gas law, and it is PV equals nRT. Well, that N is the amount or the number of gas particles. And you can think about gas particles the same way you would think about school children, you know, except they're blindfolded and running at high speed. So that is a gas particle. And I like to relate them to little kids in a gym. The first thing I want us to look at is pressure. We're going to look at pressure and temperature. So right now we have pressure of 0 degrees atmosphere because I haven't put any gas in this thing. So I'm going to put some gas in there. Come on, a little bit more. And of course, it always tells me I reached my limit. All right. So now that I have some gas particles in there, we have a temperature of 10 degrees Kelvin, and we have a pressure of 0.25. It doesn't have to mean anything to you. Like, I don't know what an atmosphere is. If you really wanted to know, it's how much pressure the air above you is exerting on you at sea level is 1 atmosphere. But you don't have to know that. Just look at that little 0.25, and I'm going to turn up the heat. What happens to the pressure as the temperature goes up? Okay, so I want you to write that down. Pressure and temperature. When pressure increases, temperature increases. What kind of a relationship is that? It is a direct relationship. One goes up, the other goes up. All right, let's look at the next one. Let's look at pressure and volume. So here we have my pressure at 14.77 atmospheres, and our volume is 1,000 liters. Well, I'm going to decrease the volume. Let's see what happens to pressure. When I decrease volume, what does the pressure do? It increases. So that's that teeter-totter relationship. One goes down, the other goes up. It's an inverse relationship. Again, let's think about this like school kids. If we have 200 school kids and they're allowed to wander anywhere on this campus, is it very likely that they will bump into each other, physically run into each other, even though they're blindfolded and running fast? No. So there's not very much pressure. Now let's blindfold 200 school kids, put them in this room. How much pressure will they exert? How many times will they bump into each other? That's a lot of pressure that's going against the molecules, going against the walls of this. That's how I think about that. So if I decrease the room size, decrease the volume, pressure goes up. All right. Pressure and amount of gas. All right, let me cool this thing off. And let me release the gas. Let me turn that off. Okay. So when I have absolutely no particles of gas, we've got no volume in there. So as we release particles, as we increase the number of particles, what happens to our volume? Yeah, your volume increases. The way I think about this is a balloon. If a balloon is just laying on the table and it's not blown up, there's very few air particles in there. Once I put it to my mouth and I blow in air particles, the number of air particles increase and the volume increases in that balloon. So that is a direct relationship. The more particles, the bigger the volume. That is pressure and amount of gas. Oh, sorry. Pressure also increases. It doesn't only increase the volume. The pressure on the skin of the balloon also increases. Sorry about that. So see, the pressure increases on the wall of the balloon as more particles go into it. And I know I accidentally just told you E2.
What's that called? Did you say that was?
Direct.
Right?
Yes, they're both direct. Yeah, the number of particles will increase the pressure and it will increase the volume if everything else is held constant. Well, let's look at volume and temperature. I'm going to lower my volume. And so now my volume is 270 liters. My temperature is 150 degrees Kelvin. So let's see what happens when it heats up. Abigail, what's happening there at home?
It's rising and going faster.
Okay, so as the temperature increases, the volume increases. Also a direct relationship. I like to think about this relationship the same way, if you've ever been to like the balloon festival up in Morgantown, when they turn on the heat, when they fire up that balloon, the volume of the balloon increases as the temperature of the air heats up. That's why it's really good to fly them on very cool, dry mornings, because then the air around them is cold, but the air inside gets heated and then it expands the balloon. Because just like those little school kids, they move faster and faster and they increase the pressure, thus they increase the volume. So how big the balloon gets is based on that heat. So that is a direct relationship. Did I miss any of those? No. Okay. All right, so let's take a look at number 2, particle motion and temperature. Actually, particle motion is exactly what gives us temperature. That's why solids are cooler, liquids are kind of medium, and gases are the hottest. So the faster a particle moves, the higher the temperature gets. So when you apply heat to it, those things speed up, those particles speed up. The hotter something is, the higher, or the faster the particles move, the hotter it gets. And it's also the hotter it gets, the faster the particles move. Those are just directly related. And what did we say about pressure? Yeah. The faster they move, the higher the pressure. So all of that is in a direct relationship. And I did attach this little website here, this little simulation to your Blackboard. So you can go in and take a look at it, play around, just to kind of help remind you of what's going on. All right, so let's take a look at number 3. We have a weather balloon, and we're going to release it from Fairmont State, and it's going to go up into the atmosphere about 2,000 meters. First of all, what happens as you go up into the atmosphere? What happens to the pressure? It gets what? More or less. It decreases. Yeah, as you get higher up there, you got less air to deal with. It spreads out. There's more and more room up there as you extend into outer space. So it decreases. The pressure decreases as you rise. So if the pressure on the balloon decreases, what's going to happen to the volume of it? If the outside pressure decreases, what's going to happen to the balloon itself? I need to bring in my little vacuum pump from the high school so you can see it. Like if we put a marshmallow in there and we take all the pressure off of it, that marshmallow is like this giant because all the internal pressure expands, it increases. So your volume as you get on up in there is going to increase because now you don't have as much pressure on the outside. This is also why mountain climbers, not just like here in the Appalachians, but you know, the Mount Everest and out in like Colorado Peak, this is why they get short of breath and why they have a hard time at high altitudes. When there is less pressure, less air pressure around you, your lungs actually kind of expand. Well, so you feel like you can't take as deep of breaths. And so they really have to train to be at high altitudes.
So the balloon will be smaller because there's less pressure around.
Actually, the balloon itself will get larger because the internal pressure, that gas inside the balloon will feel like it can finally expand. So the balloon itself will get larger because the air around it has less pressure on it. Number 4, why does an aerosol can provide a label warning against placing them in heat? Let me tell you a little story. Like I said before, I've raised 4 kids, and my nephew, who I also raised, accidentally, I'm hoping it was by accident, we have a burn pile of paper things, and somehow this is when he was in middle school, his little axe, you know how those middle school boys like axe, his little axe bottle went into the burn pile. My husband takes it outside, sets everything on fire, did not know that thing was in there. And I'm telling you, my daughters and I heard an explosion. I thought it had killed Mark. And I'm like half crying and half laughing because I was like, oh my God, what was that? And so we went outside. That stupid axe can had like blown and like, it was crazy. I was like, oh my God. So pressurized gas, even when you think those things are empty, there's still a little bit in there. There's still a little bit of gas in there. So you take gas that is already under pressure, you raise the temperature, and what happens to the pressure when temperature goes up? it increases the pressure. So you raise temperature, you increase the pressure. Those cans can only withstand so much pressure before they blow. So remember, I didn't add gas molecules to it. So that was held constant. But we increased the temperature. Then the temperature increased the volume, which also increased the pressure until it exploded. So everything varies except for the number of gas molecules. Like we didn't go outside and add extra X in there. All right, so let's see. I'm going to try to share the whiteboard and do this math problem. I know Abigail loves math. You all do, don't you? So we're going to be looking at the 3 gas laws. And we've got Charles' law first. Let me put this. And let's see here. V1 divided by T1 equals V2 divided by T2. So that's Charles' law. Then we have Boyle's law, which is P1 times V1 equals P2 times V2. And then lastly, we have Gay-Lussac's. Oops. Anyway, and his is P1 divided by T1, whoops, equals P2 divided by T2. So these are all based on relationships. And when you look at something like Boyle's law, that is an inverse relationship. Because if one side, let's say, if these two things are equal, then let's say pressure 1 goes down. To stay equal, pressure 2 better go up. And we're going to do some math to show you this. And then these would be direct relationships. But don't take my word for it. Study that. So let's actually take a look. Now, for homework, all you're going to have to do is like define these for me. So that'll be part that you do on your own because there are only like 1 or 2 sentences that define these laws. You know, they're not very intense. And mathematically, I went ahead and gave you the formula. Now on the test, you'll have to be able to like match up the formula with the, of course, guy, with the guys who formulated them, but you will also have to do the math. With the math formula, I will give you, you don't have to memorize, oh gosh, she wants me to use Boyle's law. Well, let me just pick out what I know about that. Let me do P1 times V1. Speaking of Boyle's law, let's do that right now. All right. So I'm going to try to draw this, Abigail, but no promises. So we have a gas occupies 1.56 liters. So here we go. We have 1.56. I wish this was a touch screen. And liters is actually our first volume. Whoops. It won't let me move this one. Okay, so that's our first volume. And that will be multiplied by 1 atmosphere, which is our first pressure. Now it doesn't matter which order you do multiplication in, you know that. And then it says, what will be the volume of the gas if the pressure becomes 3 atmospheres? So on this side, we're going to have 3 atmospheres. And we're going to solve for the volume. So we are solving for V2. What do I have to do to this problem to get V all by itself? Yeah, I'm going to divide both sides by 3. I'm not going to write the whole thing out. And I'm dividing by 3 atmospheres. So, whoops. So my atmospheres are going to cancel out. This was an atmosphere here. And I'm going to be left with liters. So I've got 1.6 divided by 3. And that'll give us what answer? Somebody, what is it? Thank you. We have 0.52 liters. That'll be our new volume. So more math. All right. Let's take a look at Charles' law. Now, those of you who love to cross multiply, do that on this next one. You're going to cross multiply because there are several ways to do the next problem, and I want you to choose the easiest one for you. But let me help you set it up. So we're going to calculate for Charles. Whoops. The decrease in temperature when, let's see, we have 2 liters. So our first volume is 2 liters. And our first temperature is 21 degrees Celsius. So that's the first side of the problem. And our second, volume is 1 liter. And we want to figure out what the temperature is here. So if you want to cross multiply, that's fine. I do it differently. So the first thing I do, and I don't know if you want to follow me along or not. How many of you are very comfortable with cross multiplication and found an answer? Good. Tell me what your answer is.
I didn't get the answer yet. I was just.
Okay, go ahead and get the answer before I even do my way, because I don't want to confuse people.
Was it 10.5?
Yeah, you should have gotten the answer of 10.5. Two. And well, here's what I did. I multiply both sides by T. So I get it off the bottom here. And then I have to get rid of the other ones. I have to flip it. I have to do the inverse to get rid of it. So now I'm left with 1 times, that's a multiply sign. So 1 times 21, because I want to multiply by that. And then I divide by 2 because I want to divide by that. So it's basically 21 divided by 2. But cross multiplication works. The only reason I do it the long way is because when I teach physics at the high school, they have to be able to do it the long way. So that's my comfort zone. You pick your comfort zone. Another way to do it is simply do the inverse of both sides. Because remember, whatever you do to one side, you can do to the other. So if you flip one side and put temperature on top, you can flip the other side. Because remember, it's a ratio. And what I think I will promise you is that I won't have you solve for bottom variables, simply because that's not what I want you to practice. It's not, I just want to make sure that you understand how to manipulate the gas laws. So let's go down to Gay-Lussac's. And again, you're going to see units that you might not be familiar with. Millimeters of mercury. Do you have to know what that is? No. You only have to know that that is a unit of volume. I'm sorry, that is a unit of pressure. My bad. So we have pressure and temperature for Gay-Lussac. So what's our original temperature? Okay, so that'll go in on the bottom. (323 Kelvin). And it cooled down to 273. Point, oh geez, 0.15 Kelvin. And we had our initial or our original volume, or I'm sorry, geez, I gotta quit saying that. Our original pressure was 750 millimeters of mercury. And we are looking for pressure number 2. That's a pressure. I don't know. It looks like that. Like mm for millimeters and then times mercury. It's just a pain because it's not a touch screen. All right. And so here, Abigail, how do I get my P to be all by itself?
Multiply.
Yep, I'm going to multiply both sides by 273.15. And that'll be in Kelvin. So my Kelvin is going to cancel and I'll be left with, oh my gosh, millimeters of Hg of mercury. So whatever your calculator does for you there, what did you get?
Could you cross multiply here as well?
I didn't. I just got rid of this and it left my P.
But could you to get the same answer?
Try it.
I got 634.25. That's what I got.
Yeah, I was gonna say that sounds right.
For sure. 634.25.
Because we know it's going to be lower because we lowered the temperature, so we know that the pressure is going to be lower. So that's another idea. You know, it's like, you know, does it make sense? If you accidentally doubled in pressure, but your temperature is lower, you should know that that doesn't make sense. But we'll get there. All right. And Abigail, I will upload, whoops, let me stop sharing this. I will upload, see, I don't have any video here. Can you even see me? Or you see a black screen?
Cannot. And I actually tried getting on about 10 after 12, and until 1, it just said, waiting for your host to start the meeting. So I don't know if it was on my end or on your end or what, but no, this is the first time I haven't been able to see you.
Yeah, me too. And I will upload the picture, or yeah, I'll upload the handout that I gave everybody. That way everybody has another copy of it if you need it.
Okay, I'll print it off. What is it titled? Just so I know I'm printing off the right thing.
The ideal answer.
Ideal answer. Print that off and I will fill it out. And when is that due?
All right, this will be due next Monday. You know, because oh wait, what is today, Wednesday? Sorry, that's a lie. This will be due next Wednesday. It's always a week from the day that we do it.
Okay.
So I will walk through each day step by step and label it for you. Remember, one of these days is just going to be a, hey, get caught up, read. If you haven't had time to read, maybe you can read them. And then I'll try to Zoom when I'm able to.
Next week?
Yes, I have surgery on Monday. I'll be out for 2 weeks.
Oh, I'm so sorry. I didn't know that. I hope everything
I'm
is
tough.
okay.
I'm a tough old bird.
I know you are. Heck, been in your car wreck and you know more than I'll ever know, and I don't have an excuse.
Well, listen, everybody is excused. I will, I'll wrap this up. I'll also post this little mess of a lecture, but just in case you need to refer back to it. Thanks, Abigail. You guys have a good weekend.
Thank you. So we
Thanks.
don't have class the next 2 weeks. We're on Zoom.
They're not Zoom. They're going to be individual. So thank you guys.
What does that mean, individual?
Like, I'm going to post a movie that
So we're
you're
not
going-
meeting.